And so we're going to go ahead and get started by doing a quick review of what we did at the end of class last Wednesday, because we're going to be talking about the same thing. So this is going to go relatively quick because we covered it already once, but I just wanted to go through it all and just to point it out again since we're going to be building off of that today. So last time we covered the idea of the difference between scalars and vectors. So you can think of scalars as just a single value, and you can think of vectors as, multiple values together. You can sort of think of a size 1 vector as a scalar, and sometimes that'll be a useful way of thinking about things. We also had operations on vectors. So we had things like addition, and of course subtraction is just adding by negative of each of the pieces. And you also had multiplication by a constant. So these are all standard things, and you can sort of think of these in terms of the unit plane, where addition is taking a vector and then taking the other vector after that, and multiplication is scaling things bigger or smaller, or sometimes also flipping it across. So if you take a negative multiplication. So once we did that, there are a couple different things that we covered in a couple different operations. One of them was the dot product. So oh wait, what just happened? Okay, for whatever reason, my animation is happening super weirdly with this. But yeah, so we covered dot products on vectors, where you take each of the entries of the vectors, you multiply them across each other. So the first entries of both vectors, the first entries of the second vectors, you multiply them together, and then you add them all together, and this gives you the dot product. So this takes two vectors and turns it into a single scalar. And one of the things I had you do is we tried out some examples of addition, and you note that obviously if your vectors are different sizes, you cannot add them together. Okay, and then we generalize that to matrices, which you can also add and multiply by a scalar, so you can sort of think of them as structured vectors. Where you have a two-dimensional grid of size m rows and n columns. And these have a couple other nice properties. So you have things like transpositions, where you can take the matrix and you can flip it across the main diagonal. So when I talk about the matrix diagonal, I'll almost always be talking about the one from the top left to the bottom right. Sorry, top left to the bottom right, because I'm flipped. But yeah, so why do you do a transposition? So this is going to be come up a little bit later on. But one of the reasons you might do this flip is because sometimes your matrices might not multiply together the right way. The other thing is that there are some interpretations of transpositions as sort of doing something like the opposite behavior, though we're going to make that a bit more formal later. But one easy example is sometimes you can think of a vector as just a 1 by n matrix or by an n by 1 matrix. And so this is one of the reasons why you transpose. And so sometimes you can think of a matrix with just one column, you can think of as a column vector, or a matrix with one row, you can think of as a row vector. And one of the things you can do is sometimes you need a vector to be a column, or you need it to be a row. And what you can do is if you transpose a row vector, it turns into a column vector. Okay, so the last thing I think we covered last time was this idea of matrix products, and the way I defined it was I defined it as this sort of dot product-like thing. There are a couple different ways of thinking about matrix multiplication, and we'll be trying out several of them. But here, the basic idea is that if you have two different matrices, where the second dimension of the first matrix, so if you have this, let's see, can you guys see my mouse? You guys can never see my mouse. Let me just draw on it. So if you have the second dimension of your A matrix is the same size as the first dimension of your B matrix, then you can multiply together matrices A and B. And what ends up happening is the N matrix is going to be the outer dimensions. So it's... Oh, you can actually see my mouse this time? Okay, well, anyway, yeah. I will not assume that you guys can, but thank you for letting me know. But yeah, so anyway, what we have is if you have a 2 by 3 matrix times a 3 by 2 matrix, you can only multiply them together because the 3's are lined up with each other, and so you can multiply those together. But then what happens is the end result ends up being a 2 by 2 matrix. And the reason for that is basically what you do is you take each row of your first matrix, and you take each column of your second matrix, and you multiply them together to get each of the entries of your product matrix. So here you take the first column 1, 2, 3. Sorry, first row 1, 2, 3 of your first matrix, and you take the dot product of that. So you multiply it piece by piece with each of the entries in the first column of your B matrix. And you can sort of see us doing that. Note that the last time I did this, I made a math mistake. I had this entry as a 9. It's actually a 4 if you do the math, because 12 minus 8 is 4, not 9. But yeah, so just I wanted to make that clarification. But yeah, so this is how you do this. So you take all these different, you take a row times a column, you take a row times the next column, and that's your next entry, and so on. Okay, so I'm going to make you guys try this out. So I think the chat is okay. The chat is basically set up, and okay. So I want everyone to try multiplying these two vectors, and you can tell me what you think the answer is. Okay, so we had one person who was pretty quick on the spot. Oh, well, let's wait until other people have responded. So we have 1D. Oh, I ignore the E. The E is pretty irrelevant. We have a B as well. A. Okay, so we're getting a good mix of lots of different answers. And though it looks like A and D are ahead. Let's see. How are these things coming up? So it looks like a decent number of B's, actually. Okay, so it looks like D won out, but B is a close contender, and we have some A's and one C. Okay. So it looks like this is somewhat complicated. Well, let's think this through. So the first thing you want to do is you want to look at the dimensions of these matrices, right? To see if you can multiply them together. So the dimension of this first matrix here is 3 rows by 1 column. And the dimension of this second matrix here is 1 row by 3 columns. So when you put this together, what you end up with is, well, the two, you can multiply them together since you have this 1 by 1, since the ones match up. But you end up with a matrix that is a 3 by 3 matrix. And how does this look? So what happens is you have your first row, which is just this 1, and you multiply it by the first column here, which is just this 4. And so that gives you the first row, first column entry. Yeah, so, you can change answers. If you just like change if you just enter something new, it'll replace your old answer on the chat. But it doesn't really matter. But yeah, so what happens is you have your first row, which is this 1, times your first entry, which is 4, and that gives you this 4 here. And then you have the first, and then the next thing you do is you take the first row times the second column, and it gives you this 5 here. And so on. But then you also get down to the, say, like, the second row, first column. So that's 2. Second row, first column, 2 times 4, and that gives you 8. So it turns out that this is actually, so this is a little bit tricky, right? Because earlier when I gave you vectors, I said, it looks like a dot product. But it only looks like a dot product if you do the other way. So this is why it's important to keep in mind which the matrix transpositions and which way the matrices are angled. Because if you took 1, 2, 3, 4, 5, 6, well, that would equal 1 times 4 plus 2 times 5 times 3 times 6, which is going to be equal to 18 plus 4, 22, plus 10 is 32. So that would be this one, but this is actually different because the matrices are transposed. From each of the matrices is transposed, and you end up getting a very, very different answer. So the correct answer here is actually D. Okay, so hopefully that was clear. If it wasn't, you need to practice this because this is the key thing to remember here is just keep track of the sizes and the dimensions. If you have a 3 by 1 times a 1 by 3, then you know the answer has to be some kind of 3 by 3, even if you make mistakes in the math. So let's try again. Oh yeah, sorry, D as in dog. D as in dog is the correct answer there because it's a 3 by 3 matrix. Okay, so let's give you guys another example. So let me reset this before you guys start replying. Okay. And let's see what people think this particular multiplication is. Okay, so we're starting to get a couple answers, some A's, some B's. They're both coming along. Okay, so that sort of makes sense because one matrix looks sort of like is a 2 by 2 and the other is a 2 by 1. But now the question is, which one of those is it? Okay, so we've started to get a number of responses. Let's start by breaking this down. So the first thing you should do whenever you're multiplying the other two matrices is figure out what size the solution ought to be. So here we have a 2 by 2 matrix, and here we have a 2 by 1 matrix. So yes, you can multiply these together because these 2's match up, but you end up with a 2 by 1 matrix because that goes there and that goes there. So now that means that the only possible answer here is, of course, this matrix A. And well, let's actually work it out. So we have 1, 2, 3, 4 times 5, 6. So that's going to be equal to the first column. So the first thing you're going to do is you're going to take these things and multiply them together. And so that's going to be 1 times 5 plus 2 times 6. And then you're going to have the second row and the first column. So that's going to be 3 times 4 plus 4 times 6. So that's going to be equal to, let's see, that's 12, that's 17. And 24 plus, oh, wait, did I type that in wrong? It looks, wait a moment, 24 plus 12 is 36. So it looks like I actually made a mistake there in writing it out. Did I do that right? So, did I make a mistake on, oh, 3 times 5, yes, okay, yeah. I thought okay, yep, so everyone makes math mistakes. So let's see, that's 15 plus 24, so that is 39. And so the correct answer is, oh, A here. Okay, so hopefully that was all clear. But now we've seen a couple of those. I'm going to introduce another concept, which we've already seen here, which is the idea of an outer product. I'm going to teach you a couple different ways of understanding matrix multiplication, just so that hopefully you can, one of the ways will click. So that is probably the most standard way of thinking about matrix multiplication. I'm going to give you an alternative way, which you don't need to know in order to solve matrix multiplication, but for some of you, it might click a little bit better. So we defined inner products a moment ago, right? So that's when you take two different vectors of the same size and you end up with a scalar. Now, here we had one example where you started with a 3 by 1 and a 1 by 3, and you ended up with a big matrix instead. And so that is what we can call that an outer product, actually. So, there are a couple of different ways we might write this, but we had an inner product, which is going to be, oh, that is, sorry, let me write this again. So remember, we had the inner product, where if we have two different vectors, I'm going to do these as size 3 vectors, just so I don't have to write too much. A1, A2, A3. We're going to take the dot of those, and that's going to be with B1, B2, B3. And that's equal to A1, B1 plus A2, B2 plus A3, B3. So this is a dot product of vectors. But there's another way we can think of that, because of the way we define the matrix multiplication in the products. This is actually entirely equivalent to the row vector A1, A2, A3 times the column vector B1, B2, B3. Which is equal to, well, it's a 1 by 1 matrix, but you can think of this as almost the same as a scalar. A1, B1, A2, B2 plus A3, B3. Okay, so that's an inner product. Now, now that we've defined an inner product, you might ask, well, is there an outer product? And the answer to that is yes. And the outer product, which is basically just the opposite of that. So you can think of this in terms of matrix multiplication. If you had A1, A2, A3 as a column vector times B1, B2, B3 as a row vector. So that's going to be equal to A1, B1, A1, B2, A1, B3, A2, B1, A2, B2, A2, B3, and A3, B1, A3, B2, A3, B3. Okay, so that's what's called an outer product. And you can also think of matrix multiplication using outer products instead of inner products. So I remember one of you all asked last time, could you do it with rows? Could you do it with columns instead of rows for the matrix multiplication? And the answer is yes, but you have to do it in a sort of weird way. So now let's go back to the matrix multiplication using outer products example. So I rewrote all this stuff that we had earlier. But now what happens when you take when you're trying to use outer products? Oh, could you please explain the... oh yeah, sure, let's go back for a second since I'm going too fast. So thank you for slowing me down. So basically what we have here is we have a 1 by 3 times 3 by 1, right? So you end up with a 1 by 1. But if you flip each of these, you transpose each of the individual vectors as matrices, you end up with a 3 by 1 times 1 by 3. So yes, row times column is inner, column times row is outer. And this goes back to the idea that a matrix multiplication, so when you're doing matrix multiplication like this, the dimensions really, really matter. So even though you have what look like almost the same vectors here, you just transposed both of them, you end up with a very different answer. Is there any other questions about this? So row times column is an inner product, column times row is an outer product. Can we do either? So it depends on what you're doing, right? Because both of them are valid operations, but they do different kinds of things. And so if we go back to matrix multiplication, I defined it using an inner product, right? Now the question is, can you do it using an outer product? And the answer is yes, but you have to do it in a different way. So let me go ahead and show it to you. As I said, you only need to know one of these ways of doing matrix multiplication. You don't need to know both. I personally find inner products much more intuitive. But since people were asking about whether the columns and vectors can be swapped, the answer is yes, but you have to be really careful when you're doing it. Okay, so let's go back to this example. So we did this using inner products, right? What happens if we try doing this using outer products? So let's see, 1, 2, 3, 4, 5, 6. And let's see, that's minus 3, minus 2, minus 1, 0, 1, 2. And so let's try to do this using outer products. So let's take each of the columns. And so the way that works is you take each of the columns times each of the rows. In fact, when you're doing an outer product, you only need to take the appropriate column times the appropriate row. So this is going to be 2, 5 times minus 1, 0 plus 3, 6 times 1, 2. So basically what we're doing here is we're taking this column and multiplying it by this row. So that's this one. And then we had this column multiplied by this row. And that's that one, and so on. Okay? But then note that these are outer products, not inner products. And so you end up with here, each of these, this is a 2 by 1, and this is a 1 by 2, and so on. So these end up giving you 2 by 2s. So this is going to be equal to, let's see, so 1 times minus 3, so this is minus 3 minus 2, and minus 12 minus 8. Plus, so that was that outer product, so that's this thing. And if you take this outer product, that's going to end up being, let's see, that's minus 2, 0, minus 5, 0, plus, and the very last one here is going to be 3, 6, 6, 12, which is equal, when you add this all together, it's going to be minus 2, 4, minus 11, and 4. Okay, so yes, the answer is you can do matrix multiplication using outer products. Most people find it more easier to do it with inner products. So you take each row and column, multiply by every other row and column. But if you take a column and multiply by the appropriate row and then add that together, you also get the same matrix multiplication. These sorts of ideas will become much more important if you actually study linear algebra later on. So some of you who are in mathematical biology may end up doing all kinds of SVDs and singular value decompositions for data analysis later on. So there's a lot of linear algebra and numerical data analysis. If you end up doing that, you may find it useful sometimes to think about matrix multiplication using outer products. For the purposes of this class, we are going to be mostly focusing on the inner product interpretation. But I just wanted to throw this out there for those of you who were interested. But now, let's go back to what matrix multiplication means. So if you remember, we had this example here, where if you take a square matrix and you multiply it by a column vector of the appropriate size, you end up with a new column vector of the same size, right? So that means we can sort of think of matrices as transformations of vectors. And let's actually, could you go back? Okay, yeah. So let me stay on this slide while I talk a little bit more. So you can think of matrices times a single vector as a transformation of that vector if you have a square matrix. It turns out that you can think of this interpretation even if you have non-square matrices, if you have rectangular matrices, but it's easier to think about in the context of just a square matrix times a column vector of the appropriate size. And so that's what I'm going to be talking about on the next slide, which is that matrices can be thought of as transformations of vectors. So, for example, if you had this matrix here, so this is a very simple matrix. It's a diagonal matrix with 2's on the diagonal and 0's everywhere else. If you multiply this out against some arbitrary vector xy, so that can be any point in the xy plane, all you're doing is you're multiplying all the points by 2. So this is a transformation where you're scaling everything up. And so if I draw this out, that looks a little bit like, let me draw this out. So if you started out with a vector, let's say here, then this transformation would scale it out past it, so it'd double it. You start with a vector here, then the transformation would double it. And you can sort of think about these things as scaling entire shapes as well. So here we've drawn vectors as lines, but you can also think of vectors as just single points in space, right? So if you had a circle as your original point, if you scaled every single one of those points by doubling by 2, what you'd end up with is a doubled circle. Okay? So that's the most basic kind of matrix operation. You're taking each of the coordinates and you're scaling them. And this is a powerful way of thinking about matrices, because what they're doing is they're taking some coordinate and transforming it into some other coordinate. You can also do more complicated transformations, like squashing and stretching. So in this case, what I've done is we have two coordinates. We have x and y, right, on the xy plane. And we're going to squash the x-coordinate and stretch the y-coordinate. And so what this will look like is if you start with a point here. If we start with this point here, what we're going to do is we're going to squash it in along the x-axis. So remember, this is x and this is y. And we're going to stretch it out along the y-axis. So this is going to end up being, oh, sorry, that didn't quite work out. We're going to stretch it out along the y-axis. And so if you think about applying that to a circle again, that's going to end up giving you something that looks like this ellipse, because we've squashed it in and stretched it out. And let me give you one final example of this sort of transformation. You can also do rotation. So this is a little bit more complicated. Instead of just like squashing and stretching, you can also rotate things around. So if we have, say, a point. So this here is going to be a 90-degree rotation. I've just constructed as that. You start with a vector here, that's going to turn it into the vector here. Is it stretching and squashing because it's a decimal? So it's basically if you multiply by something that's less than 1. So if you think about it, what this matrix is doing is it's multiplying each of the coordinates by some value. So it's squashing because it's multiplying one value by something less than 1, so 0.5, and stretching because it's multiplying something by a value greater than 1, which is 2. So you're stretching when you multiply by something bigger than 1, and you're squashing when you multiply by something less than 1. In this case, we are just rotating, so this is just a rotation. And because it is not very interesting to rotate a circle, I'm going to rotate a rectangle instead. So let's say that we had started with this rectangle here, and then what's going to happen is we're going to rotate this entire thing. And so that's going to give us a new, the rectangle is going to be rotated 90 degrees. And there are all kinds of different transformations. So these are just the most basic types of transformations that you can do with a matrix. But you can think of a matrix as applying some transformation to a vector. And this, how is the y and x switch play? Oh, how do the y and x switch places? Yes, so this is matrix multiplication, right? So if you look at, let me circle this. So if you take, oh, sorry, that clicked the wrong place, transformations. So if you take a look at this very first row, and you multiply by the first column, what do you get? You end up getting minus y, right? Because there's a 0 in the top left, and so 0 times x plus minus 1 times y. So this ends up giving you minus y. And the second row gives you 1 times x plus 0 times y, and so that ends up swapping the places of the x and the y. It turns out that these types of matrices that cause you to swap places, people study these particular types of transformation matrices that either rotate or permute things around. So in theory, the first one, 2x, 2y, is stretching both sides by 2. Yes, exactly. So the first one is stretching both the x and the y by 2, and so you end up getting just a easy scaling. So you can think of a scaling operator as just a subset of stretching and squashing. I'm just giving you some examples of like the different ways these things can look. Really just stretch the same. Yes, so you can think of it as really just stretch the same amount in both directions. And there is an entire theory behind understanding what is stretched and squashed and what's rotated, and we'll be getting to this, well, actually next week, because we'll be getting to eigenvalues and eigenvectors. So it turns out that most matrices you can think of as stretching some particular axis. So here I made easy examples that did things to the x and y coordinates, but there are other examples that let you stretch like different axes that are just offset. And so that is the entire theory behind eigenvectors and eigenvalues. They tell you what vectors are being stretched and what vectors are being squashed and what vectors are being rotated. How does rotation relate to stretching and squashing? So this is one of those things where you get the black magic that is complex numbers. So rotations are related to stretching and squashing because you can think of a rotation as a scaling in the complex plane. And this is going to be a little bit more complicated to get to, but we'll talk about this next week. So I don't think I want to talk about it quite yet. But for now, you can think of it as a different type of operation. But it is related to stretching and squashing. Okay, so let's move on from that. And let's get back to some biology, because this is a mathematical biology class. So how do these transformations apply to real biological examples? And here, I'm going to introduce something called a Leslie matrix. So consider you have a rabbit population, and rabbits we're going to divide them into two age classes, young and adult. It turns out that rabbits reach sexual maturity really, really quickly, often within 6 to 7 months. This is why you get phrases like breed like rabbits. And adult rabbits can live on average for around 9 years. So you can encode the size of a rabbit population into, so like when you're asking how many rabbits are there, well, you can say the total number, which is just the scalar, right? So maybe you have 1,000 rabbits, and next year you have 2,000 rabbits. But sometimes it's important to understand the population at a more structural level. So instead of just 1,000 total rabbits, maybe you have 900 young rabbits and 100 adult rabbits. So you can consider a state vector or a population vector of the rabbits. And so you might consider encoding in both pieces of information, number of young rabbits and number of adult rabbits, into two different coordinates of a vector. And so this allows you to build more nuanced models of the rabbit population. So let's suppose that each year, both the young and adult rabbits have a chance of surviving, and if a young rabbit survives, it becomes an adult rabbit, and they have some number of offspring. So they have kids, and so they have baby bunnies, and you can encode that in something called a Leslie matrix. And so we're going to encode several different things here. So fecundity is just the number of offspring you get. And so young rabbits, because they reach sexual maturity within half a year, over the course of a year, they may still have kids. And of course, adult rabbits are definitely going to have kids. And then you also ask how many of them survive. So the number of kids in the next generation is going to be the number of the young rabbits times how many kids they have, plus the number of adult rabbits times how many kids they have. And the number of adults in the next generation is going, in the next year, is going to be how many adults survived, plus how many young survived. And so we're basically encoding all this information into these matrices. And once you've done this, it turns out that we can do this, think of this as a matrix transformation. So if you take a look at this matrix, which we call Leslie matrix, and you multiply it by this matrix called this population vector matrix, what you end up getting is what I just described. So the top vector is going to be the number of offspring of the young rabbits plus the number of offspring of the adult rabbits. And the second half of it, the bottom coordinate, is going to be the number of surviving young plus the number of surviving adults. So that's going to be equal to the number of young rabbits the following year and the number of, oh, I misspelled following. That is following, for the record. So number of adult rabbits the following year. So what we're basically saying is that by using this Leslie matrix, you can predict the number of rabbits the following year based off of doing the sort of matrix multiplication operation. All we're doing is we're multiplying matrices together, and that allows you to evolve the system from the first year to the second year. Let's give a numerical example. So let's suppose that we had a Leslie matrix, which is going to be equal to, let's say, 2, 3, 0.5, and 0.9. So what we're saying here is that the average number of average number of offspring for a young rabbit is 2, whereas the average number of offspring for an adult rabbit is 3, and that young rabbits have only a 0.5 chance of surviving, but an adult rabbit has a 0.9 chance of surviving. So this is our Leslie matrix, and then what we're going to say is the year 1 population, we're going to have some number of young and some number of adults. Let's say that this was 100 and say 10. Okay? And we're going to write this as a matrix. So then if we want to figure out how many rabbits there are in year 2, all we have to do is we have to take L times, let's give this a name. Let's call this vector, let's call it X. Oh, no, let's call it P. Sorry, I used X in my earlier notes, but let's call it P for population vector. So LP, so L times P you can think of as a matrix. So this is going to be 2, 3, 0.5, 0.9. And we've written the population vector as a column vector. So that's 110. So if you multiply this out, what you end up getting is 230 and 59. So this means that in year 2, you expect to have 230 young rabbits and 59 adult rabbits. So this gives you a model for the growth of the rabbit population, assuming that everything works out on the average. Obviously, when you're applying this in real biological scenarios, there's going to be some amount of noise and randomness. But this model allows you to give the amount give at least some estimate of how many rabbits there are the next year. What if you do it again? Well, if you want to know how many there are in year 3, all you have to do is you take 2, 3, 0.5, 0.9, and you multiply it by what there was in year 2. So you multiply all these numbers together because the number in year 2, so we can also rewrite this as L squared P, because you're multiplying by L twice. But it's often easier to do this one step at a time. So this is just equal to L, 2, 3, 0.5, 0.9, times, we already know what LP is since we computed that. So that's 230, 59, So here this is L again, and this is LP, since we computed that in the last step. And this is just going to be equal to 637 and 168.1 if I did my math correctly earlier when I was making my notes. So this is going to be L squared P. And that's going to be the number of adult rabbits, young rabbits, 637, and a prediction for the number of adult rabbits, 168.1. Obviously, you can't have 0.1 rabbits in real life. This is just a mathematical model, but this is an estimate of how many rabbits you expect there to be in year 3. And you can keep on going. So this allows you to evolve the number of rabbits over the course of multiple years. Let's see. How do we know that each one, when we multiply, it is per year and not per month? So that is just part of the model. So we've defined it as the Leslie matrix for a year jump. So that's part of the definition. So you have to, if you wanted to, you could probably come up with a matrix for each month, but it would obviously be a different matrix. And so if you're a biologist, one of the things you might do is you might say, oh, I'm going to measure the population year after year, and then that allows us to get the entries of this matrix. So I'm giving you this matrix, but of course, if you're a biologist, you have to measure each of the different components in this matrix to figure out whether the numbers are right. Can you do LP again? So just here for LP, we had this matrix L. So L here is the Leslie matrix, and you multiply it by your P vector, which is 110. So here you have 2 times 100. So 2 times 100, which is 200, plus 3 times 10, which is 230. And so on. So you're basically taking the row times the column and taking the next row times the next column, and that gives you the 2 entries. So this is standard matrix multiplication, which you should practice. One other thing I should mention, in case people, all the things that I have in text, basically, I have in the pre-lecture notes on the website. So if you have trouble following when I just put lots of text on, that is all available on the website. Let me let's switch to that quickly. Pre-class notes. So if you go into the lecture 3B, lecture 3A pre-class notes, you'll see that I have basically everything that isn't written. So if you have trouble keep writing down all these things, you can just go look at the PDF. And of course, I'll put a PDF of everything I've done after class with my writing. Okay, so hopefully this answers you guys' questions. And this is basically the reason why, one of the reasons, there are many reasons why matrices are powerful. This is one of them. It allows you to take a system and then you and evolve it to the next state, because you can think of a matrix as a transformation on the vector. Now, obviously, this transformation is a lot more complicated than the scaling or stretching ones that we saw, or rotation ones that we saw in the last slide. But these are still the same kind of transformations, and there's an entire theory to understanding how these transformations work. Would year 1 information be given to us if we were to get a problem like this on the exam? That is a really good question. So there are several different types of problems that you might want to answer. One of them is, if you have a Leslie matrix and you know what it is in year 1, maybe what is it in year 2 or 3 or 4? And in that case, I would obviously have to give you year 1. There's another type of problem which we'll be covering in the second half of this today's class, so after the break, which is going to be, if you have year 2, can you figure out what year 1 is? What is the definition of a Leslie matrix? So this Leslie matrix is just this transformation matrix that tells you this is just the matrix that encodes this average number of offspring and the average survivability. So basically it tells you how many members of this population turn into or give rise to members of this other part of the population. So how many new young rabbits do you have because you had 5 young rabbits and 10 adult rabbits? So this is sort of, basically this encodes in both offspring and survivability. So fecundity and survivability is the standard way that you talk about these Leslie matrices. So this is a 2x2 matrix. You can get Leslie matrices that are much bigger if you have multiple different states. So for example, if this were, maybe you could divide it into baby rabbits, young adult rabbits, and adult rabbits. And in that case, you would have a 3x3 matrix that would encode both fecundity and survivability of each of the different stages to the next stage. So it varies a little bit depending on your model, but that is the basic idea behind the Leslie matrix. Leslie matrices are only for populations, yes. But there are comparable transformation matrices that you'll see in other applications. So it turns out these sorts of transformation matrices play a role throughout mathematical biology as well as chemistry. But the Leslie matrix in particular is specific to what's called Leslie's age-structured population model, which is the specific type of population model we're talking about right now. Okay, so let's move on. There are a couple different ways we can encode the Leslie matrix. One of them, which is quite useful, is we can encode it as a graph. And this graph is sometimes a little bit easier for you to understand what's going on. Because, like, well, if you just give a matrix, that's not really a picture of what's going on. But if we have this matrix, L is equal to 2, 3, 0.5, and 0.9, one of the things that you might encode it into is as a graph with two nodes. So this here is going to be node 1, which is going to refer to the young. And this here is going to be node 2, which is going to be state 2 in the vector, which is adults. And what we're going to do is we're going to draw arrows depending on what direction things go. And so the way we'll do this is we'll take this arrow, and that's going to be a circular arrow from node 1 to itself, because this is how many young there are as a result of each young member of the population in the previous generation. And then you do the same thing with your 0.9 here, 0.9. And then what you do in each column is you look to see, here, this is row 2, column 1. So this is going to be the number of adults next year as a result of having each young. And so this is going to be 0.5. And here, this is going to be the number of young as a result of each adult. So you can encode, and if you had a 0, you just wouldn't draw an arrow. But you can sort of encode this to give you a sort of graphical overview of how the Leslie matrix is acting on your population. So if you had, say, 100 young here, then you'd multiply it by, if you had, say, 100 young here, then you'd multiply it by 2 to get the number of new young as a result of those 100 young. And then you multiply by 0.5 to get the number of new adults as a result of your 100 young rabbits. And if we want to try this out, you can sort of see this, because the number of young next year is going to be equal to 2 times the number of young plus 3 times the number of adults. So this is exactly the same information that's in your matrix. We just encoded it as a graph, because sometimes it's easier to see like what direction the population causes other parts of the population to grow. And you have number of adults next year, which is equal to 0.5 times the number of young, because that's the number of young who survived to become adults, plus 0.9 times the number of adults, since that's, well, just the number of adults that survived. And one of the things you'll note is that if you look here, the arrows that come out of a node are precisely the entries of the column corresponding to the node. So here you have these 2 arrows, 2 and 0.5 coming out of node 1. And so that's why you get this 2 and 0.5. So entries of column 1. And so could you please explain that again? Yeah, so the basic idea is if you take each of the entries in the first column, so the first column here corresponds to the first node, okay? So the first column, and this is first node, okay? And the second column corresponds to the second node. And then what you do is, for each of the entries here, this here is row 1, column 1, right? So then you draw an arrow from node 1 to itself. This here is row 2, column 1. So you draw an arrow from 1 to 2. And that's this arrow here in green, because you draw an arrow from 1 to 2, and it goes from column 1 to row 2. And you do the same thing for the second column. So the second column, the 3 here, this 3 here is row 1, column 2. So you end up with an arrow going from 2 to 1. And that's this arrow here. And so on. And the 0.9 goes from row 2 to column 2, and so, or sorry, column 2 to row 2, and so you end up with the last arrow of 0.9. And this is just an alternate way of thinking about Leslie matrices. So all we're doing is we're taking this matrix and turning it into this diagram with arrows pointing in the directions that they're causing things to happen. And this is a common thing you see in biology where you draw out this diagram. And often, in this case, it doesn't seem to make much sense to draw this diagram, right? Because you're just repeating all the same numbers. But if you have a lot of zeros in your matrix, which you often will, if you have a lot of zeros, then you can just ignore that arrow and you can see sort of the direction that the population evolves, which is the reason behind these sorts of graphs. Okay, so, of course, this is a confusing topic, so it is time for you all to try it out. So, oh, I didn't draw my Leslie graph yet. So, I am going to give you an example where you have a population of birds, not rabbits this time, but birds have hatchlings and adults, and you have similar behavior. You start with 100 hatchlings and 40 adults, and I'm going to give you a Leslie diagram. So here, this is hatchlings, and let's say this here is adults. And let's say I have an arrow 0.5 here. So for each hatchling, you end up with another half a hatchling the next year. And for each hatchling, you end up with 0.75 adults the next year. And for each adult, you end up with 1.25 hatchlings the next year. And for each adult, you end up with 0.25 hatchlings the next year. So, given this Leslie diagram, I want you to compute how many hatchlings and adults there are the next year. And let me reset this. And so, which of these is the correct number of hatchlings and adults in the following year, in year 2? And so what you're going to have to do is you're going to have to take this Leslie diagram, turn it into a matrix, and then multiply the matrix by your population vector. And I'll give you guys a couple of minutes to do this. Well, I might give you a hint because this seemed a little bit difficult for people. So one of the things you're going to start out with is you're going to need to figure out what L is. So what is this matrix? And you're going to need to figure out what P is. What is this vector? So P is going to be relatively easy, right? Because that's just going to be 140 because hatchlings and adults. This L matrix is a little bit harder because you need to look at each of the entries of each of the arrows and turn them into an entry in the matrix. Okay, so we've started getting a reply. We got one person who thinks that it's D. Let's see, thinks it's B. Okay, so that's switching from D to B. Well, let's go ahead and work this out together since we're running a little bit short on time. So if you have 0.5 and 1.25, so 0.5, oh sorry, let me actually do this in order and explain what's going on here. So you have 0.5 because you have an arrow from 1 to 1, and then you have 0.75 because you have an arrow from 1 to 2. And then 1.25 because you have an arrow from 2 to 1, and 0.25 because you have an arrow from 2 to 2. And so you multiply these together, so LP is going to be equal to, well, that's going to be 50 plus 50, and that's going to be 75 plus 10, which is going to be equal to 185. So yes, the correct answer is B, which it looks like people managed to get. Oh, sorry, the thing didn't update in... Come on, Zoom. Ah, there it is. Okay, so people got that right. So the basic idea is once you have this matrix, all you have to do is you just have to do matrix multiplication. So now that we've done that, let's talk a little bit about a couple other standard properties of matrices, and then we'll take a break. So let's start by talking about the identity matrix. So this is a special n by n matrix such that when you multiply by any other matrix, you get it back. So, of course, you have to have the right number of dimensions. So this is n by n, so you can multiply it either by an n by m matrix if you multiply it on one side, or an m by n matrix if you multiply it on the other side. And this matrix is really easy. It's 1s along the diagonal and 0s everywhere else. And this has some super nice properties. Basically, if you have 1, 0, 0, 1, 5, 2, that's going to be equal to 5, 2. And this doesn't matter And this also works if you have different shaped matrices. So 1, 2, 3, 4, 5, 6. This is just going to be equal to 1, 2, 3, 4, 5, 6. So you should think of it like multiplying by 1. So if you're in the scalar, multiplying by 1 doesn't change anything, right? If you're in a matrix, multiplying by the identity matrix doesn't change anything. And in fact, if you think about it, if you have a 1 by 1 identity matrix, it is just 1. And so this is the natural generalization of multiplication by 1, is multiplying by this identity matrix. And there are a couple other properties of matrix algebra, which we should go through. So there are a couple other properties. One is that if you multiply things together, it doesn't matter what order you multiply them in. So if you have, say, 1, 0, 0, minus 1, and 1, 2, 3, 4, and let's see, 5, 6, you can multiply them in two different orders, right? So if you multiply these two together first, you end up with, this is going to be 17 and minus 39. And then you multiply it by this 1, 0, 0, minus 1, and you end up with, oh, sorry, that's 17 and positive 39. You end up with 17 and minus 39. And if you do it the other order, so let's do it in the other order. If you multiply these two matrices together, that's just going to be 1, 2, minus 3, minus 4. And you should double check my work there, times 5, 6. So that's going to be equal to, again, 17 and minus 39. So it doesn't matter which order you do them in. Another property is the distributive property, if you have A times B plus C, that's equal to AB plus AC. And so let's see this quickly. So if we have, let's say 1, 1, 0, 1 times 1, 2 plus 3, 4, this is equal to 1, 1, 0, 1 times 4 and 6, which is going to be equal to 10 and 6. On the other hand, it's also equal to, if we do it the other way, that is not the right color because that is the highlighter. If you do it the other way, you end up getting 3, 2 plus 7, 4, which of course also equals 10 and 6. This distributive property also works the other way, so if you multiply on the other side, but I'm not going to write this out, but it's basically the same idea. But one super important thing to keep in mind when you're dealing with matrix multiplication, AB is not equal to BC in general. We've already seen this a couple times with like different size matrices, but even if you have the same size matrices, you're not necessarily going to have them be equal. So let's give a super simple example. 1, 1, 0, 0 times 1, 1, 0, 0 times that. So that's going to be equal to 2, 0, 0, 0. On the other hand, 1, 1, 0, 0 there, and where the ones are in the left side, and 1, 1 on the top, 0, 0, that's going to be equal to 1, 1, 1, 1. And these are not equal. So make sure you remember that most properties are similar, but AB is not equal to BA. Sometimes they'll occasionally happen to be the same, but usually they're not equal. So I will leave you for the break with a couple examples. What just happened? With a couple examples, and I will stop recording and we'll come back and look at these afterwards, but we'll also be moving on to the next lecture. So you should try these out and see what you get. And let's come back at 1:20 after the break.